there we go. Okay, so let's move this up a little bit. Okay, so drawing first, we had a starting point. Let me get my... Okay, so let's draw this out. All right, so we had our first vector 12. So I'll make a north, south, east, west grid. Since we're going to be going towards the east, I'll put it over here. Okay, there it is, north being at the top here. Okay, and then my vector is going to go straight north. So I'm going to just do it in blue. And I'm going to go roughly, what did I say, 12. All right, and then when we get there, we have to put another north, south, east, west grid line down so that we can put the direction of the next vector there. Okay, so let's label that vector 12 meters. Okay, then my next vector went to 7.5, and what did I say it was there? South, 40 degrees east. So here's our east direction. So we're going to draw that vector in with our arrow. Let's get an arrow in here. Still getting used to using the tablet. Let's do it in green. Okay, so 7.5 would be about here maybe. 40 degrees maybe there. Okay, so this is 7.5. And this is 40 degrees. Okay, so that means we have our resultant vector going from here to there. So we draw in our resultant vector. I'll just use a dotted arrow. Okay, so then we can see that we have a side angle side to get this side. Okay, we'll call this one was A here. This one was B. So that, or sorry, little b, little a. We're going to stick with cosine law rules. Little a, little b. So that would make this angle right here A, this angle down here B, and I'll call this little r. So this is big R up here. Okay, so we're going to do the cosine rule around these three values here. So the cosine rule, we want to get r. So r squared equals 12 squared plus 7.5 squared minus 2 times 12 times 7.5 cosine of 40. Okay, that's the pattern. Okay, if you don't know the pattern, you can just label it all out and use the formula sheet. Okay, so going along here, we've got 144 plus 56.25 minus 137.89. So when I get that, I get r squared equals 62.36. Can't read my own writing here on the side. 63, and so we get an answer of 62.36. So when we do that square root, I get two significant figures, unless if we did 3, did I do 7.5 or 7.50? 7.5? Okay, so 2 significant figures then. So that would be 7.9 meters. Okay, and then to get the direction, we want to get this angle down in the corner here. How far is it going towards the east from north? So we now know that this side R is 7.9. So we have a relationship between the 40 degree angle R and the side R's. And now we need a relationship between this side and angle B. So we do a sine law here. So we got R over sine R, okay, equals B, angle B, or side B, sorry, 7.5 over sine B. Okay, so if we do our multiplication, 7.5 sine 40 equals, or sorry, this is 12.9. 12 point, oh boy. Oh no, I got it right there. I'm confusing myself. And then we're going to multiply 7.9 and what is it here? 7.9 and sine B. Sorry about that. Okay, so far so good. Everybody agree with me? Okay, so I got to do a divide. I didn't work this one out because I ran out of time this morning. Okay, so we'll just divide that up. Okay, so let's do 7.5 times the sine of 40. And then I'm going to divide by 7.9. So I get 0.6102 for my sine B. Inverse sine that. And I got about 37.6. So if we're doing two significant figures, we can say 38 degrees. For B. So our final answer is right here. We got 7.9 meters, and our direction is north, 38 degrees east. Of course, if you did the other direction, it'd be 90 degrees different. Okay, so 90 minus that would be 52. Okay, any questions on that one? Okay, so that's basically what we were doing yesterday. So the very last thing in this mathematical approach to vectors that we have to do at the beginning of motion, because most things in physics are vectors, speed isn't, but velocity and acceleration and displacement are. So the next thing we're going to be looking at is there is a second way to add skew vectors, and that's by breaking vectors into components. So we're going to look at what is a component of a vector, and we're going to only look in two dimensions. Okay, so we look at that north, south, east, west grid mainly. Okay, when you get into higher education, or if you get into higher education that deals with the sciences, you'll be doing 3 dimensions, which makes it way more fun because there's 2 reference angles instead of 1. Okay, so that, especially if you enjoy, I don't know if you're like me, and you enjoy breaking things down and figuring things out. University physics, not in the first year, but maybe in the second year, gets to be really fun because there's lots of mathematical breaking down, and then there's a lot of what would I call it? A lot of physics that isn't really. It's more a theory. There's a theoretical physics that comes into place. So I'd encourage you to at least test it out when you go into school. All right. So let's get into our final topic in vectors, and that's components. And components are rather simple. If we look at things in terms of the north, south, east, west line, and we equate it to math, we can just call them y and x components. Being the x line, we represent our east-west line, and our north-south line represented by y. So let me just type this in here. So components of vectors. Okay, so basically what it is this. Every vector will project a partial vector or a component component. Oh boy. Okay. We'll project the component along the X and Y axis. It might not be both, but it might just be one, right? But it could be both. So when we say X, we mean the east-west line. And Y. Sorry, I should put the word axis in there to be more specific. People in Vanguard know, students in Vanguard know that I'm atrociously terrible at spelling and other things. English is not my thing. So, my apologies. And this would be the north-west, or north-south line. Okay. Okay, so for example, if we were to draw this out, so let's say that the vector is, let's say my vector, let's say we have vector Q equals 200.0 meters south, 38 degrees west. Okay, so we can draw this vector in our north, south, east, west line. Oops, let's not do it in dotted. Okay, so if we just draw this vector, so this vector is going to be going south and then west. So down here somewhere. So here we have our vector. Let's use a different color so it looks a little better. Okay, and about 38 degrees out here. Okay, so if this is our angle here, and this is north. Okay, so now we know both angles here because this is 90 degrees, but I'm going to use the angle that's that's given to us. We now have a projection here of y. So if I take my arrows and I'm going to do a dotted arrow here, and I'm going to use two different colors. So this one is projecting along here, and then this one is projecting along here. Let's use orange. Okay, so there's our projections. There's two projections. One's projecting down and one's projecting out to the left. So if we label these up, if we call this one here vector Q, this component we'll call, because it's along the x-axis, if we moved it up here, but it's projected in it's parallel to the x-axis, we call this our QX. Sorry, that's theta. I get so used to drawing thetas. It's not a theta. It's QX. So this is QX, and this one's QY. That's an X. Okay, and that's basically how you get your vectors. Now, how you get your vector is if you know that this is 200.0 meters, we know that this is a right angle. We just use sine and cosine. And it changes depending on if your angle's with the y-axis or with the x-axis. So it's not always the same. Sometimes you use sine, sometimes you use cosine, depending on where your angle is in that specific area quadrant of the north-west or north-south, east-west lines. Okay, since we've got it with the y here, this is our opposite side and this is our adjacent side. Okay, so to get the component QX, okay, it's Q times, right, times, because QX is the opposite side and you're going to do opposite and hypotenuse that sine. Okay, QY, that's going to be Q times the cosine of the angle, because you want the adjacent side. It's the adjacent side. Now, if it was over here and you're using this angle, it'd be different. Okay, so you can just figure that out. 200 times the sine of 38 degrees and 200.0, but I'm just writing 200 times the cosine of 38. Just take our calculators out, figure them out. Okay, so you go 200 sine 38. That's 123.1 because I got 4 significant figures. And then the other one, 200 cosine 38. And that's 157.6. Now, of course, because this is a direction, we could write the directions on them, east, west, north, south, right? Or if we want to be even lazier, we could just use north could be plus and south could be negative in the y-axis, and west could be negative and east could be positive. So then all we have to do is decide, well, that's going down. Down is negative in the y. And that's going backwards. Backwards is negative. And then we know that that negative x means it's actually pointing towards the west. Right? So we can equate, physicists or mathematicians or whatever, we don't want to write 123.1 west. We want to write negative 123.1 because it's faster. So you always put the sign into your component based on your traditional math quads that you use in your grade 10, 11, 12. Well, actually 9, 10, 11, 12 math. And you remember that this is still north, south, east, west. Okay, so that's our component, sorry. That's basically what a component is. Okay? You can have it here, you can have it here, you can have it here. It can be any one of those 4 quadrants. Okay, this one has, both of them are negative. This one here, we have a negative value in the horizontal and a positive vertical, or north it'll be north and back to the west. Of course, this is positive, positive, that's north and east. This is positive for the horizontal and negative for the vertical, so that would be east and south. So that's how it works. Don't forget though, if you have a component like this, so we're going to do adding to, so let's do vector j as well, and I'm going to do it underneath. But I'm going to set up a vector j where we're going to actually have it not with the, I'll give it to you so that this angle is with the x-axis. So we're going to start with east or west first. And then we're going to add the 2. And that's basically going to be it for today, really. Okay, so let's go ahead and say that vector j is, let's say it's 160.0 meters, so that we have 4 significant figures. And our direction this time is going to be, let's go east, 57 degrees south. Okay, I'll let you work those components out, and I'll work it as well. Okay. I'm going to draw mine here, and then I'll work it as well. And then we're going to add the two together and find the resultant vector using component methods. So this method is, you're simply going to break them into components and add components together, and then reform it. But I'll let you get the components of that vector j. So just call them jx and jy. Now don't get messed up. The angle is going to change with the x-axis, so that's going to change your sine and cosine. Oops. Maybe I'll use a different color for the axis here. Anybody missing today? From Great in Vanguard? Oh, okay. Okay, so 160, so it's shorter than the other vector, east and then south. So east is this way here, and south is still down. So I'm going to pop my vector in there. Let's put it as a different color. Okay, but my angle is 57, so maybe something like that. Okay, put my angle in. Put my size in. And then maybe, what are my projections? You don't necessarily have to draw them, but I like to. Why? I don't know why, just the way it is. So let's use the dotted line here. There's one. If I went a little too far. There's the other one. So this would be jx and jy. Okay, now you'll notice that because we have it, the angle here instead of here, your opposite and adjacent change. Like that. So that when you're doing this, let me do this with a skinnier line so it's easier to see. Like, so this jx we'll do over here. That's going to be j 160. Okay, but this time it's adjacent and hypotenuse. Adjacent is cosine. Okay, we'll work it out later. So this one, if we look back up here, the x is cosine. Last time the x was sine, because we changed the position of the angle. It's with the different axis. So it can change and it will. Just showing both of those. Okay, so, and then jy, we're going to be looking at 160 again. Meters. Okay, this time we're looking at the opposite side, so opposite is sine, 57. Okay, four figures. Let's punch it into our calculator. 160 cos 57. You should have got 87.14. Probably round that to just one decimal later, but keep the significant figures for now at the beginning of the year. And then 160 times the sine of 57. 134.2. Okay, now we have to decide, based on where they're pointing, whether this is a positive or a negative. Okay, so let's take a look at the x. Well, the x is pointing forward or towards the east, so we'll convention say that's positive. Okay, and again, y is still pointing down. That's negative or south. Okay, so that basically is the first two steps if you're adding two skew vectors. If you're adding two skew vectors in this method, this second method, is you break them into components. Okay, so we'll summarize that. Before I go on, because all I can hear literally is crickets, right? Is there any questions from anybody? Or is this reasonably good? Good? Okay. You guys? Pretty good. It's just sine and cosine. Okay, so what we're going to do now is we're going to add vector j to vector q. Okay, we did the first two steps already, but I'm going to summarize it as if we haven't, but we have. So we're going to add those together. So our idea here is adding two skew vectors. We're going to add j plus q. So step one, find all four components. Okay, so we did okay, so we did that already. We broke them down into components. Okay. Okay, so if I go back here, we've got our four components. I'm going to write them out on the last page based on what we solved. So Q was 123.1 and 157.6. So, sorry. Let me get my marker out again. So Q, X, Q, Y, and then we had, what did I call the other one, J? Right. Okay, rather than me look back, so what was QX again?
123.1.
120, it was a positive or negative?
Negative.
Negative? Okay, and what was QY?
157.6, and it's also negative.
And it's also negative. Okay, and what do we have for JX?
87.14, and it's positive.
Okay, and that was the only positive one.
Yeah.
And then last one, JY?
134.2.
134.2 negative. Okay, so now it's very important to keep the signs. So what the signs are telling us is whether they're an east or a west, a north or a south pointing vector. So you need to keep them. Okay, so that was step one, is to break it apart. Step two is to combine the two x components and two y components together for both vectors. So step two, combine. Now you could, honestly, this is the only method where you, well, not the only method. This is a method where you could add 3 vectors or 4. You just have to break them all into components and total them all up. So combine all the x components together and combine all the y. Okay. Okay, I'm lazy. Not generally in work, but lazy in writing, because historically for me, I I missed most of grade 1, most of grade 2, and part of grade 3. I don't like writing. Sorry, hasn't changed in 55 years. But, so this just means it's the same words. Okay. So now that we've got all the components, we're going to add them together. Now we need to signify what our answer vector is going to be. I call it R. So R is going to be our resultant X vector. So this is going to be negative 123.1 plus 87.14. Okay, so we take our calculator, we go 87.14, and we subtract 123.1, or you can use negatives, and we get 35.96 negative. Now, when you're adding and subtracting significant figures, you always go to the adding and subtracting is different than multiplying and dividing. Multiplying and dividing, you keep the same number. Adding and subtracting, you go to the highest uncertainty. The highest uncertainty is a tenth. So we're only going to go to the nearest tenth. So this is going to be 36.0 then. Negative. Okay. Now, I'm not a stickler for significant figures as much as some other people. So if you're around, if you kept it at 35.96, I wouldn't mark it wrong because it wouldn't change the answer in the end. But I'm just illustrating that keep your significant figures. Any of you that are going to go study physics or particularly chemistry at a high level, say a couple years into university or tech school, they will expect you to know how to do those significant figures. If you're rusty on significant figures and you want me to review that, let me know and I will do that in some class with you, okay? If you're not really sure how that works. Okay, I'm going to call the resultant vector of y. So these are both negative, so it's going to be a negative one. So 157.6 minus another 134.2. Okay, so this is going to give us whatever it gives us, 157.6 negative plus 134.2 negative. Okay, so that's 291.8. Again, they're both tenths, so that round to the nearest tenth. And this is negative again. Okay, so now you have both your components combined together. Now, if you were subtracting vectors, this is where you would subtract them. But we're just doing adding. We haven't done any subtracting at all. Generally speaking, for subtracting, you just change the sign direction. So now in step 3, we do a right triangle now to get the resultant vector. We combine x and y in a right triangle like we did on the second day of class where we were looking at, or maybe it was the first, I can't remember, perpendicular vectors. Now we have perpendicular vectors. This thing here, well, negative x, well, we know that negative x is what direction? West. Negative y is what direction? South. So we're going to draw a south vector and a west vector together. Now, which one you draw first does not matter. So step 3 is to form a right triangle. So you can go ahead and work it out. I'm going to work it out here, but if you want to go ahead and try it on your own, go ahead. Okay, so let's go ahead and draw this out. Okay, so you don't have to have a grid system. It's just north, south, and east, west. So I'm going to draw my starting point right here. Okay, I'm going to go west first. And then south next. And here is my beautiful straight line vector here, R. So this is 36.0, negative of course, but we don't need to put the negative in there if we know that it's west now. and that this is south. Okay, now I'm going to warn you, don't put the signs in at this point. That sign does not mean size at all. That sign means direction. So when you're dealing with size, that negative means nothing. It means direction. So when you're trying to find the size of the vector, which is what we're trying to do right now, we'll get the direction by finding this angle up here. Okay? So keep it at just, even if you do, we're going to square them so it'll drop out. I'm just bringing that up so that we know that. So we're going to go 36 squared plus 291.8 squared equaling r squared. Okay, get your calculator out. 36 squared plus 291.8 squared. Okay, that's a whole bunch. And then square root it. Okay. Okay, significant figure wise, we're going to go to, we're doing squaring and then adding and subtracting and dividing. So there's only 3 here. There's 4 here, so we've got to go to 3. So I get 294.0 or 294. So there's our size of our vector. Okay. Now we have to get a direction. So we want this angle up here. And if you drew south and then west first, then you would have the angle over here. But we can get both of them. So now we're going to use in step 4, finding the angle. For our direction. Okay. Okay, so let's go ahead and do that. So this is going to be tangent. So we're going to take the tan theta, and that's going to be the 291.8 over the 36. So she's going to be a nice big number in there. So we're going to take that and go and inverse tan that. You can change it to a decimal if you want, or just put it in brackets on your calculator. You know, back in my day, when I was your age, which would have been, what do you guys, 17, 16? So that would have been like 1984. We didn't have inverse calculators. Well, we did later on, but we still used tables most of the time in books. Okay, so let's go do that on my calculator. Second function tan of 291.8 divided by 36. Close that up. And we get 82.96, so I'm just going to round it off to 83 degrees. And then we have our answer. So this particular vector addition for r is 294 meters. And it's going to go, according to what I did in my diagram, I went west first, then I went south. If you did it the other way, it would be south and then 7 degrees. It would have been a smaller angle. Okay. Okay, so that ends today in terms of instructional stuff. So I am going to, tomorrow's going to be a work period, or tomorrow, Monday's going to be a work period on some practice. I'm going to leave you a component practice one to work on for the last, whatever we got, 15 minutes. But once you get that done, you don't have to stay online with me. I'm going to stop the video at this point. But I'm going to give you two skew vectors to add together using components. So let's say we have, try this one. Let's say A is 2,340, so that's 3 significant figures, meters, and we'll say that it's going north 25 degrees west, and you're going to add B, which we'll say is another vector, and we'll say that that vector is 1,650, so 3 significant figures again. And you can go to the nearest degree because the degrees is 2 significant figures, but the size go to 3 significant figures. And we're going to go, let's go north again, but we'll go 40 degrees east. Okay, so there's something to work on. Use components. Okay, I will start there on Monday. And also, on Monday, you'll want to, maybe before class or at the very beginning of class, or right after we do this practice, you'll maybe print out some sheets here in Vanguard. I'll print them out for you. But I will choose one person to make sure that I send them it an email just in case they can't get into the Google Classroom in your school. So somebody there, I'll tell you who when we log in. All right, so we work on that. I'm going to stop the video at this point.